Yeah, welcome back, everyone. So this morning, it's my great pleasure to introduce our first plenary speaker. So we have Jonah Blasiak from Dresser University, and Jonah will be telling us about Catalonia. Thank you, Jonah.
Hello? Can you guys, is this loud enough? Maybe not, huh? Hello? Okay. Put this a little higher. All right, hello? Okay, so, all right, again, thank you to the organizers for making this happen. It's nice to finally be at an in-person conference. This is my first one in several years. Okay, so I don't think the mic is working. Oh. Hello? I have to put it a lot closer, huh? What was that? It wasn't picking up. Okay. Oh. A different shirt, yeah, maybe. Let's see. Hello? Not quite, huh? Maybe if I talk louder? No? Okay. All right, so let's get started. So the first thing I want to define for you is going to be sort of an object we'll talk about throughout this talk called root ideals. So we'll let R plus denote, will be an index set for the set of positive roots of GLN, which we'll identify with the squares above the diagonal in this n by n matrix. Okay. And a root ideal is just an upper right justified subset of boxes in this R plus, okay, as in this example. And maybe you can guess sort of how many root ideals are there for GLN. Well, this turns out to be the nth Catalan number. Okay, so here the Catalan number 3 is equal to 5, and here are the 5 root ideals for GL3. So perhaps you're familiar with the more common thing that enumerates Catalan many objects, Dick paths. So if you take the bottom sort of left border here of a root ideal, then you get, and rotate it 45 degrees, then you get a Dick path. Okay, so I want to start off giving you just a preview of actually the last slide of the talk. So this is really maybe more properly a future work slide, but I thought it was kind of fun to start off with this. So consider the following sort of intriguing question. There are a lot of formulas in Lie theory and in symmetric function theory which involve some kind of product over all positive roots. So here are some examples. Some of this notation we'll define later. There are Hall-Littlewood polynomials, Cauchy formulas for Schubert polynomials, and so on. And the question is just, well, what happens if you take this product over all positive roots and replace it with a product over a root ideal, a smaller subset, rather than the full set of positive roots? Okay, and well, maybe something interesting happens. So I don't know. The case that we're going to talk about mostly in this talk is the case of these what are called modified Hall-Littlewood polynomials, and we'll go through the definition in just a second. But so it seems like kind of an interesting question, especially from I very much like the sort of heavily experimental style of algebraic combinatorics. It's easy to compute these and see what you get. And because there are so many root ideals, it kind of gives you a lot of examples for experimentation and figuring out general patterns. So this is kind of going to be a theme of the talk. All right, so let's get into the definition of Catalan functions, and then we'll sort of go from there about connections between these objects and various other classes of symmetric functions. Okay, so we're going to work in the ring of symmetric functions in infinitely many variables, capital X is equal to x1, x2, and so on. HD is the Deth homogeneous symmetric function with the following conventions. And so Schur functions indexed by partitions form a basis for the ring of symmetric functions, but it's useful to have a definition for integer vectors. So any vector gamma in z to the n, we're going to define this S gamma of x by the following sort of version of what's called the Jacobi-Trudi formula. Okay, so this is our definition of the Schur function indexed by any vector. All right, so it's going to be important to know for our next definition how to compare this to the usual sort of Schur functions which are indexed by partitions. And this result sometimes goes by Schur function straightening. So, and it actually sort of follows pretty easily directly from this definition as a determinant. But so let's just say what happens on an example. So if I give you, say, gamma is 3125, here's the recipe for deciding what this Schur function sub gamma is equal to. Well, you add the vector rho, n minus 1, n minus 2, and so on. In this case, you get 6335. If you have a repeated part or a negative part, then the resulting Schur function is 0, okay, as in this example. On the other hand, if you say take gamma is 4716, we add rho, we get 7926. We have distinct non-negative parts. Then you sort this and subtract rho, and 6552 is the resulting Schur function, the straightened Schur function. Okay, and it comes with a sign depending on the number of transpositions we needed to do this sorting. Okay. All right, so here's the definition of a Catalan function. This is going to be our sort of basic objects we're going to work with throughout this talk, and will be sort of a prototype for other things. Okay, so we're going to define the Weil symmetrization operator to be the linear map sigma from Laurent polynomials to symmetric functions, which just takes a Laurent monomial z to the gamma, which is z1 to the gamma 1, and so on, to the corresponding Schur function indexed by gamma. Okay. All right, so this is kind of just a bookkeeping device here. And we define the corresponding Catalan function to be the Weil symmetrization of z gamma times this product of 1 minus qzi zj over zj. And we need to interpret this as we're going to expand these as geometric series, 1 plus qzi over zj plus q squared zi squared over zj squared, and so on. Okay, and that's going to give us an infinite series, but it's not hard to show that sort of only finitely many terms will survive once you do this Schur function straightening, and you'll get an honest symmetric function out. Okay, and I'll give an example of that in a second, but first let's say what the two extreme cases are. So if you have no roots, well, then you're just left with z gamma here. There's nothing here, and that's just back to just Schur function straightening. If gamma is a partition, then that just ends up being the Schur function S mu. Okay, so that's familiar. The case of the full root ideal, where you take all positive roots, is sort of a well-studied case. These are known as the modified Hall-Littlewood polynomials. I'll have a few slides on that in a minute. Okay, but let's do an example first to see how this definition sort of plays out. Is the sound still bad? Kind of. Okay. All right. I'll try to speak up a bit. Maybe I can hold this mic. Point it toward me. Okay. All right. So here's an example. So we have these three roots, and we like to sort of draw our Catalan functions in this way, where the weight is displayed along the diagonal, and the roots are displayed in red like this. Okay. So here is this product expanded out, and now we need to expand all these factors as geometric series. Okay. And so here's what we get. So there are infinitely many terms here, but because of this stipulation that when you have your exponent vector, when gamma plus rho has a negative part, then you end up with the Schur function straightens to just 0. So you throw those out. And sort of here are the terms that are not obviously 0. And now you have to apply Schur function straightening to these to get the answer. So for example, this 63 minus 1, 1 ends up, when you do the Schur function straightening, ends up becoming 6300 times minus 1. Okay, and it's going to cancel with this guy here. So those two terms will cancel out. And okay, so for example, this 64 minus 1, 0 ends up Schur function straightening to 0. All right, so what you're left with is some Schur positive expression. And it's kind of miraculous that this happens because, after all, there's cancellation here because of the signs that come up in Schur function straightening. Okay. All right, so we'll talk about this Schur positivity more. All right. So now I want to tell you a little bit about these modified Hall-Littlewood polynomials. Remember, these form one of the extreme cases of Catalan functions. Okay, so first thing is when you set Q to 1, these give you the homogeneous symmetric functions that we mentioned earlier. So this H mu is just the product of HDs. Okay, and their Schur expansion coefficients are called the Koska-Folks polynomials. When you set Q to 1 here, you just recover an ordinary Koska coefficient, okay, which is the dimensions of weight spaces of an irreducible representation of the general linear group. All right, so these Koska-Folks polynomials were first studied in the 50s and 60s in work of Green and Hall and Littlewood on the character, related to the character theory of GLN-FQ. And they've sort of since come up in many different places in combinatorics and geometry and representation theory. To name just a few, they happen to be equal to certain affine Kasdan-Lustig elements. They have a nice description as what's called the graded Frobenius series of certain quotients of this ring. So graded Frobenius series is just a natural way to encode an SN module as a symmetric function where you take the irreducible representation indexed by lambda and you turn it into the Schur function indexed by lambda. Okay, and what is this ring of covariance? So this is a polynomial ring quotiented by symmetric functions, the ideal generated by symmetric polynomials of positive degree. This turns out to have dimension and factorial. It's some graded version of the regular representation. And this by itself gives you h1 to the n, okay? And if you want to get the other h mu's, then you have to take further quotients of this. All right. So there's a nice combinatorial formula for these in terms of semi-standard tableau and a statistic called charge due to Lescaut and Schutzenberger. Is it possible that there's some setting here that will raise the volume? Okay, well, maybe it's... I don't... Maybe. Hello, is this better? Okay, all right, so I would just want to show you a little picture of this Lescaut-Schutzenberger result. All right, so maybe let's go to this one here. Okay, so the result says that this modified Hall-Littlewood polynomial of shape, for example, 2, 1, 1, is given by its Schur expansion, well, is written down here in one notation, but this is kind of another way to think about it in terms of tableau. You take all semi-standard Young tableau of content 2, 1, 1, meaning there are 2 1s, 1, 2, and 1, 3. And then there's a certain statistic called charge, which you can put on these, and that tells you which the Q power here, which I've sort of displayed as a height here, okay? So this is kind of a picture to keep in mind for the modified Hall-Littlewood polynomials. These are going to come up in a couple of ways in this talk. Okay. All right, so now to just give you a brief account of some of the sort of broader context of Catalan functions. Okay, so as we've seen, they contain the modified Hall-Littlewood polynomials. They also contain parabolic generalizations of these, studied by several groups around 2000. So the parabolic in this case, if you want to think about the root ideal, that corresponds to the case where the set of roots are the ones above some block diagonal matrix. Okay, and so this case turns out to be very interesting. There was various work done involving tableau combinatorics, affine de mesure characters, variations of Jing operators, and so on. Another interesting class of symmetric functions that the Catalan functions contain are the K-Schur functions. That's what I'm going to get to next. Okay, so this is just to sort of illustrate that this is a very rich class of symmetric functions that contains many that have already been studied. Okay. They also have a geometric description in terms of as graded Euler characteristics of certain vector bundles on the flag variety. And because of this, if you can show that they're sort of alternating sums of cohomology, so if you can show that higher cohomology vanishes, this automatically gives you a proof that they're sure positive, okay? And that was shown in some cases by Brouwer, Haig, and Penyushev, that higher cohomology vanishes, and therefore the Catalan functions are sure positive. We eventually resolved the sort of major open question about Catalan functions conjectured by Licheng Chen and Mark Heyman in 2008. We were able to prove that all Catalan functions of partition weight are sure positive using affine crystals. Okay. I'm not going to get a chance to tell you about that today, but I'm going to talk more about some sort of precursors to that work. Okay, so I want to start by telling you, or I want to now tell you a little bit about the story of how these were connected to K-sure functions, okay, and just a little bit of history of the K-sure function. So these arose in studies of the Macdonald positivity conjecture by LaPointe, Lescaut, and Morse around 2000. We'll talk a little bit more about Macdonald positivity later. So just to get a sense of sort of, well, what kind of class is this? These are symmetric functions indexed by partitions whose first part is at most k. And when you set Q as 1, there's a nice description of sort of the space they span. They form a basis for the subalgebra generated by H1 up to HK, those homogeneous symmetric functions. Okay. And later, Lamb and LaPointe Morse connected these to affine Schubert calculus, right? This is kind of a remarkable connection. They came up in theory of Macdonald polynomials, were eventually connected to something totally different. It turns out they represent Schubert classes in the homology of the affine Grassmannian. One consequence of this is that their structure constants give you Gromov-Witten invariants, which generalize the Schubert structure constants. They're multiplicative structure constants, so you multiply two and expand in the same basis. Okay. All right, so a lot of work was done on these K-sure functions over the years. So I want to tell you about the following result we proved around 2018 of realizing these K-sure functions as a subclass of Catalan functions. This was conjectured by Licheng Chen and Mark Heyman. So the kind of main thing I want to focus on here, and that I want to sort of kind of continue into the remainder of the talk, is this construction of a very special root ideal. Okay, and that this will kind of be a prototype for how the combinatorics of root ideals is a very convenient way to kind of encode a lot of information into a polynomial, okay? In a way that's convenient for proving combinatorial things about it. All right, so here's the construction. So we take a partition mu of length less equal n and the first part less equal k, and like say mu is 6553211 and k is 6. Okay, and we're going to again draw our Catalan function with the weight along the diagonal, the root ideal in red, and the rule is the following. So we say that in each row, this weight, 6, plus the number of non-roots has to be equal to k, which in this case is 6. So here there's 0 non-roots. Here we have 5 plus this one white square, that's 6, right? Here 3 plus the 3 empty squares is 6 again. Okay, until you get to the bottom where there are no roots in that row, and then it's okay to be less than k. Well, that's why this is just in quotes, but it's sort of the right way to think about it, I think, or the easy way to think about it. Okay. All right, so this is kind of a very special construction of this root ideal, and a lot of nice things follow once you have this definition. Okay, so we were able to connect this Catalan, to show that this Catalan function is equal to the corresponding K-sure function, and here are some results we were able to get out of it. So the first was quite surprising and not previously known. We call shift invariance. It says that if you take this symmetric function operator en perp and act on a K-sure function, then you get another act on a K plus 1 sure function, you get a K-sure function indexed by the weight where you subtracted 1 everywhere. Okay. And like kind of one demonstration of why the kind of Catalan function realization of these is useful is just that it made this sort of result immediate. And if you go back to the definition of the root ideal, what it comes out to showing is basically, it just comes from the following fact. So if I take this weight and I subtract 1 everywhere, well then the mu I plus number of non-roots in each row is just going to be 1 less everywhere, right? It's going to give me k minus 1 now instead of k. And that property of this root ideal is really directly what leads to this nice identity. And using that, we were able to establish that the k-Schur functions have positive branching coefficients in terms of k plus 1 Schur functions. And by iterating this branching sort of onward, eventually you get down to Schur functions, and it proves that the k-Schur functions are Schur positive. So these were previously sort of important open conjectures. Lamb was able to establish these at Q as 1 using geometric methods, but this method in addition gave an explicit positive combinatorial formula for these coefficients. Okay, so this was our sort of first demonstration of really how this kind of Catalan function approach could be quite powerful. All right.
Can I ask, what's the relation between this Q and the McDonald Q?
What's the relation between this Q and the McDonald Q? So when you, in terms of the original origin of k-Schur functions, when you expand the McDonald polynomial in terms of k-Schur functions, then the Q in the McDonald and the Q in the k-Schur are the same. I mean, you can pick Q or T because it's sort of symmetric, but so it's like the k-Schur functions are sort of graded in only one direction. The McDonalds are graded in 2, and you're sort of slicing up the McDonald into these pieces, right? And so the coefficients you get in the expansion of McDonald's into k-Schurs will have Q's and T's in them. Yeah. Okay. All right. So I now want to just say a little bit about sort of where we're headed in this talk. So once we, back in 2018, sort of I'm going back to our mindset after we proved this result. So we had this nice result on k-Schur functions because of realizing them as a subclass of Catalan functions. So it was sort of natural to ask, well, can we extend this kind of idea to other settings? Can we do some kind of QT version of Catalan functions that would then, say, prove McDonald or give a positive formula for McDonald polynomials? Now, we don't know how to do that, but that's kind of the one goal that we were looking at. And since then, we've sort of found a number of ways in which we can extend this idea of sort of finding other variants of Catalan functions and realizing nice symmetric functions as a part of that class, okay, just like we did for the k-Schur functions. All right, so that's what I want to tell you about in the remainder of the talk. But before I do that, I want to say a bit more about sort of why it's nice to realize, say, a class of symmetric functions as a subclass of Catalan functions. Okay, so like in this previous result, well, this is we got something nice out of that, but I want to kind of get to the heart of sort of why it's nice to realize a symmetric class of symmetric functions as a subclass of Catalan functions. And maybe the sort of first and simplest reason for this is just that there are so many Catalan functions, right? There are a lot of them because there are so many root ideals. So maybe more precisely, for a fixed degree, there are sort of only partition many k-Schur functions, right, of that degree, but Catalan functions, you can vary the weight and the root ideal. So there are many more, and having so many more allows you to have sort of stepping stones between the individual elements of your chosen class of symmetric functions. And having these stepping stones enables an inductive approach to things like Schur positivity. Okay, so I'm going to now tell you about a sort of specific implementation of this idea. Okay, this idea we call root expansion. We later learned that this idea was first appeared in the work of Buch, Kresch, and Temvakis in a sort of different setting on Schubert calculus of the orthogonal and symplectic Grassmannians.
So maybe that's all the more reason to believe that this is a sort of interesting approach. Okay, so here's what happens. All right, so we're going to start with the following proposition. Given a Catalan function, like this one on the left, we're going to write it as the sum of two Catalan functions. And the way that works is we have to choose some root alpha, which is sort of an outer corner in some sense of this root ideal. So in this case, there's only one outer corner. By that I mean it's sort of, I can remove it and I still get a root ideal. Okay? And it's easy to show directly from the definition of Catalan functions the following result, that this Catalan function is equal to the sum of two, one where you remove the root and the other where you change the weight by adding one in the row corresponding to the root and subtracting one in the column corresponding to the root. Okay? Okay, so now there are a few different things that you could potentially do with this, but let's sort of focus now. Suppose we want to show a given Catalan function is sure positive. Well, we can iterate this root expansion. So here's our first step. Now let's say we take the left one and we expand on this root. So there's a choice here. This is not a unique tree. At each step we have to choose a root, an outer corner to expand on. Okay, and so here we remove that root, and then in this right node, we added one to the second part and subtracted one from the third part to get weight 332, 0, just to sort of save space. You'll see why we need to save space soon. You can delete, when you have a 0 on the end, you can delete that entire column. Okay. All right, so here, and now let's do the right-hand side. So here this Catalan function expands into two. One where we delete the root, one where we change the weight. And now this is the first instance we have of a Catalan function of non-partition weight. And that's potentially problematic because if you start computing with these, you'll quickly see that Catalan functions of non-partition weight can easily be not sure positive. Okay, so once you get something like this, you're potentially stuck and you don't have a proof of sure positivity anymore. But it turns out that sort of if you're lucky and you choose your roots to expand on carefully, then you'll always sort of run into a Catalan function that's 0 before you run into one that has positive and negative terms in its sure expansion. Okay, and this Catalan function turns out to be 0. All right. So it's not hard to prove from the sure function straightening, for instance. All right, so here's the whole root expansion tree. Okay, so right, you just keep doing this until you get down to leaves, which eventually are equal to sure functions, right? When you have no roots, these are just sure functions, and except for some of them are 0. So some of them end up being 0 because of this, same thing I told you over here. And basically, you can read off the sure expansion from this tree. Okay, so, and also the Q power. So the number of times you go to the right tells you the Q power. Okay, so it's actually still an open conjecture whether it's possible to take any Catalan function of partition weight and find a tree like this to prove that it's sure positive. But we know how to do this in several kind of classes. So one, the sort of maybe first class that we found that where this works is where your root is a rectangular root ideal. And here I mean by rectangular, I want it to be sort of like all the way touching the diagonal here. This is using like this definition. Then in that case, when you set Q to 1, you end up with a product of sure functions. So in this example, you sort of split this into two pieces. This is equal to S32 times S21 when you set Q as 1. Okay. And so it turns out using root expansion, you can recover a kind of Littlewood-Richardson rule. It's not exactly the usual Littlewood-Richardson rule, but it's even possible to sort of trace down these paths and give an explicit tableau that's something like a Littlewood-Richardson tableau. Okay, yeah?
When you add the Q's, does that translate to some sort of Littlewood-Richardson rule for like, I don't know, maybe all Littlewoods?
Yeah, so when you add the Q's, so does that translate to some Littlewood-Richardson rule for Hall Littlewoods or something like this? So, and the answer is yes. So with the Q, it also has a nice meaning, and there's a sort of analog of a product of Schur functions due to Shimazeno and Zebracki that has a Q in it, and so it does give you a Q version of the Littlewood-Richardson rule. There is a catch there, which is that you can't iterate it with this method. So you can only multiply once, and which is potentially an issue sometimes. But anyway. Okay, so now another reason I wanted to tell you about root expansion is because it forms kind of the core of this proof of this sort of important result that I mentioned, that the K-Schur functions are a subclass of Catalan functions. So, okay, so just a little bit, a couple words about this proof. So let's just temporarily call this right-hand side the K-Schur Catalan function, since we don't yet know they're equal, okay? And so to prove this, we had to connect these K-Schur Catalan functions to a definition of K-Schur functions involving strong Bruchau order on the affine symmetric group, okay? And kind of the meat of the proof is that you have to take one of these K-Schur Catalan functions indexed now by something that's not a partition weight. It's close to a partition weight, but not quite. You get to subtract one somewhere. And interestingly, this definition still makes sense, right? So this is part of this kind of theme I was telling you about. There are so many Catalan functions. That's important. Before, with just K-Schur functions, there would be no way to make sense of this, a K-Schur function indexed by something that's not a partition. But here, we automatically have a definition of this, and this serves as a sort of stepping stone. We use the root expansion on this and show that it's always equal to a K-Schur, like one of these K-Schur Catalan functions indexed by a partition, or 0, okay? Okay, so again, right, all the intermediate objects here really help proving things by induction, okay? All right, and another kind of cool thing here is that if you didn't know about Bruchau order of the affine symmetric group when you started this, like working with this combinatorics of the root expansion here kind of forces you to rediscover that. They somehow miraculously line up exactly like they need to. Okay. All right. So for the remainder of the talk, I want to now tell you about some kind of extensions of Catalan functions where we were able to take this. Okay, so can we find some version of Catalan functions that works for symmetric functions in 2 parameters? Okay. And yes, we have, and I'll tell you about that in a second, but I want to just introduce these a little bit. So Macdonald polynomials originated in the 1980s with studies of Macdonald on certain symmetric functions called Jack polynomials. So there are sort of 2-parameter generalization of something called Jack polynomials, as well as the modified, or as well as Hall-Littlewood polynomials, a certain variant of these modified Hall-Littlewood polynomials. These functions studied by Macdonald are often denoted P, Q, or J in the literature. We're going to work with a variant called the modified Macdonald polynomials, which Garcia and Heyman worked on a lot in the 90s. These are denoted H tilde mu. And sort of here's a picture. So here's H tilde 3, 1. Here's its Schur expansion, and then here's sort of the picture where we write T powers on the y-axis and Q powers on the x-axis. Okay. And I think it's kind of a good way to sort of keep a picture of this in your head is this is a natural generalization of a modified Hall-Littlewood polynomial, a sort of a 2-parameter generalization where if you take the, say, Q is 0 slice, that's this vertical slice here, you get the corresponding modified Hall-Littlewood polynomial. If you take the T is 0 slice, you get the modified Hall-Littlewood corresponding to the transpose partition, okay? And sort of then you have to, then the rest gets filled in somehow, right, with these, Macdonald polynomials are hard. There's no known way to do some kind of Lescaut, Schutz, and Berger rule here to get some combinatorial formula for the Schur expansion, okay? This is still an important open question. Maybe one little thing to notice here is there's always a row Schur function here and a column Schur function at sort of the opposite extreme, just to kind of keep the picture in your head. Sort of studies of Macdonald polynomials often were surrounding the Macdonald positivity conjecture, which in this notation states that these Macdonald polynomials are Schur positive. And this was eventually proven by Mark Heyman around 2000 using the geometry of Hilbert schemes. He was able to show that the H tilde mu's are the bigraded Frobenius series of certain Sn submodules of this polynomial ring in now two sets of variables. So here, Sn acts by permuting the x's and y's simultaneously. And there's a way to define certain Sn stable submodules here. You take a certain determinant in x and y's, and then you take all partial derivatives of that, and it gives you this Sn submodule whose character is the Macdonald polynomial. Okay. All right, so that's just a brief introduction to Macdonald polynomials. Another sort of important player in this story of Macdonald polynomials is called the Nabla operator. So the Nabla operator is defined to be the linear operator on symmetric functions whose eigenvectors are the Macdonald polynomials and whose eigenvalues are given by t to the n of mu, q to the n of mu prime, where n of mu is this sort of well-studied statistic on partitions. It turns out that, so here's a picture. Okay, so this is Nabla applied to E3. Nabla on En turns out to be a very interesting and Schur positive symmetric function. Okay, so maybe just notice a couple of things here. So in the q is 0 and t is 0 slices are the same, and these are actually equal to the Hall-Littlewood 1 to the n, okay? 1 to the 3 in this case. Another thing to notice is that if you count these Schur functions indexed by a single column, or maybe you count them over here, you get 5 of them, and this is a Catalan number, and that turns out to be true in general. Okay, and actually, I don't know of any precise or any sort of connection between the way Catalan functions show up here and the way they do the way Catalan numbers show up here and the way they show up in the definition of Catalan functions. So this seems to just be two sort of separate instances of Catalan numbers showing up. Anyway, so also using geometry of Hilbert schemes, Mark Heyman was able to establish that this Nabla En is equal to the bigraded Frobenius series of the diagonal co-invariant ring. This is the quotient of this polynomial ring in two sets of variables now by the ideal generated by symmetric polynomials without constant term. Right? If you remember back to the modified Hall-Littlewood polynomials, it was almost the same definition, but with just one set of variables. Okay. All right. So what's known about the Nabla operator? So I attempted to sort of cram sort of everything that's known about the Nabla operator into a single slide, and I have certainly failed. And I apologize for sort of all the work that I left out. But I just wanted to sort of show you a little glimpse of this. There's been an awful lot of work done on sort of studying the Nabla operator applied to various classes of symmetric functions, okay? And one of the miracles is that Nabla applied to many well-studied classes of symmetric functions like En, Pk, even the Hall-Littlewood polynomial, Schur functions, turns out to be Schur positive, well, up to a global sign at least. Okay, so here, these are not quite Schur positive, but up to some predictable global sign they are. Okay, and not only are they Schur positive, but they have sort of beautiful combinatorics, and an awful lot of work over the last 20 years has gone into studying this combinatorics. So the first thing that was looked at was Nabla Ek, this was, so Garcia and Haglund first studied this, where they were able to show that the coefficient of the Schur function indexed by a single column is given by the Catalan number. That was what we talked about on the last slide. And then sort of building off this, Haglund, Heyman, Lohr, Remmel, and Ulyanov were able to conjecture a formula for Nabla Ek in terms of what are called LLT polynomials. So in this case, the LLT polynomials are certain Q analogs of elementary symmetric functions, and you have one of them for every Dick path in a K by K rectangle. Okay. There are several other this was eventually proven by Carlson and Mellett in 2015. Interestingly, it ended up using a sort of refinement of the original shuffle conjecture of HHLRU regarding nabla of H lambda. Okay. Other variants involve something called the elliptic Hall algebra, where now this combinatorial side involving Dick paths in a K by K square gets replaced by Dick paths in an M by N rectangle. Okay. So many more generalizations. The representation theory is more difficult. Okay, so there's been a lot of work on trying to find representation theoretic models for these. Here are a few that I know of. So there's the one we talked about on the last slide was due to Mark Heyman, and there's a similar kind of description of nabla to the M. There's a result of Hikita connecting some of this sort of MN version to affine Springer fibers. Okay, so anyway, just give you a picture of sort of really how much work has been done here. And now I want to tell you about, in the last few minutes, about sort of how you relate these to Catalan-style objects. Okay, so we're going to define the following, called a Catalanimal. So this is a variant of a Catalan function, where now there are three root ideals, RQ, RT, and RQT. Okay, and the RQT comes in the numerator now, and the RQ and the RT are just sort of like before. They're but now they have a Q and the T coefficient. Okay, so here's an example. We choose RQ and RT to be R plus, and so this is all the positive roots. RQT is just this one root, 1, 3. Okay, so here's this expanded out again. And again, we have to expand these as geometric series and then apply Schur function straightening. And okay, so here's what we get in this case. This turns out to be equal to, well, it's almost nabla of E3. It's omega on nabla E3. Okay, and this turns out to have a generalization, this example. So here's the following construction. So let's call this the nabla En Catalanimal. So what we do is we take RQ and RT to be the set of all positive roots, and RQT to be all the roots except this sort of main diagonal's worth, okay, as it's shown in this legend. And we take the weight to be just all ones. And what we were able to show is that building off of work of Nagu and Schiffman-Vasterot on the shuffle algebra, that this Catalanimal is equal to omega nabla En. Okay. I think I'm running out of time, so I will just be very brief about this next construction. So there's a really nice construction of a similar kind of thing for nabla S lambda, involving sort of nice combinatorics of the shape lambda, kind of gets mapped in a nice way into certain combinatorial construction of these root ideals RQ, RT, and RQT, as well as the weight. Okay. Luckily, my collaborator, George Seelinger, is going to tell you more about this in the next talk, so I think I'm going to skip over the details here. But you can at least see a sort of picture to get maybe the idea that there's some interesting combinatorics involved here. Okay. Okay. So we were able to show that this sort of specially constructed Catalanimal, based on the original shape lambda, is equal to omega nabla S lambda up to some constant. All right. So here are some results that we obtained out of this. So first of all, we ended up with a new proof of the shuffle theorem, as well as a sort of generalization of the shuffle theorem to, rather than just paths, sort of shuffle theorem involves Dick paths over a K by K rectangle. Then there are generalizations to M by N rectangles. This involves sort of lattice paths under any line. We were able to use this to give a proof of the Lohr-Warrington conjecture involving a Schur positive, that gives a Schur positive formula for nabla S lambda. And so the thing that we used here for all these examples was a certain Cauchy formula involving non-symmetric Hall-Littlewood polynomials. So the sort of, in terms of like how much work goes into this, well, sort of a significant fraction of the work was getting this Catalanimal for, say, nabla S lambda, and then there's another sort of big step to use this non-symmetric Cauchy formula to get out certain sure positivity results from this. Okay, so all right, so some other outcomes of this, we were able to prove the extended delta conjecture of Hagelin, Remmel, Wilson. This involves a generalization of the nabla operator called the delta operator, which also there's been a lot of work done on. And something George will tell you about is a sort of Catalan-style formula for the modified Macdonald polynomials. These are not quite Catalanimals, but something kind of close to them. Okay, so now I want to just go over some of the things that we were able to find sort of using this idea of taking some objects that involve product over positive roots and then altering that set of positive roots to be over just certain root ideals. So, you know, we talked about these K-short Catalan functions. There's also a sort of K-theoretic version of this construction. And then we have these nabla S lambda, nabla En, and then George is going to tell you about some more general versions of this nabla on an LLT polynomial, sort of Catalanimal style formulas for the modified Macdonald polynomials. Okay, so these are all sort of nice Catalan-y kind of objects that we were able to find for various well-studied classes of polynomials, or of symmetric functions, rather. Okay. And so just to sort of say now where this might be headed. So I think it's kind of miraculous that we're able to find sort of so many different formulas like this, right? Like, it's not clear that there should be any such formulas. And so now it seems like a natural thing to try to do is to try to look for this in a lot of other places. So that goes back to this slide that I previewed to you earlier. But maybe before we get there, let's think about, okay, so if you have such a sort of Catalan-style formula for a class of symmetric functions like Macdonald polynomials or something, well, what can you do with it? I mean, so I've mentioned that, you know, there are several ways you can sort of use that formula to get access to various properties of these symmetric functions. One are using these root expansion techniques to maybe prove sure positivity, and the other are these Cauchy formulas, okay? But in both these cases, it's somehow very useful to have all these extra intermediate objects. They really help you with sort of computer experimentation of piecing together a picture of what's going on, okay? And so I'll just end with this, this slide. Okay, so now what happens if we replace this product over positive roots in sort of all these different examples that we see, right? So there's, so right there, there's various ways of kind of getting at this first pursuit, right? So in the cases that we looked at, for example, the nabla En, right? We kind of just had to engineer this by hand. We're like, okay, so we want some Catalanimal style or Catalan function style thing that gives nabla En. What properties must it have? Okay, and sort of it was hard work in every case, but maybe now that we sort of have enough of these examples, maybe it's possible to piece together some kind of more general phenomenon. And so it seems at least plausible that this could lead to something interesting of just taking some of these formulas, and it's also just kind of fun, experimentally, take some of these formulas and replace this product of positive roots with product over root ideal and see what you get. Okay, so I'll end there.
Thanks, Jonah. Thanks for the interesting talk and keeping the perfect timing. Yeah, we have 5 minutes for questions and answers. Oh.
I might have just missed this, but when you said the charge formula for Hall-Littlewoods,
Yeah.
is there a charge formula for the Catalanified Hall-Littlewoods or the features?
Oh, so the question is there a charge formula for the Catalan functions, I guess? Is that? Yeah, so those are what we call the Catalan function, that's right. And the answer is yes, there is. So that's this result that where we were able to prove the sure positivity of any Catalan function of partition weight that I didn't have a chance to tell you about. This is using affine crystals. So it turns out that if you take a subset of those Lescouche and Berger tableaux, which are cut out by a certain rule called catabolism, then you take t to the charge, s sub shape, sum that up, then you get the Catalan function. Okay. But the charge statistic is the same as the original one. Yes, that's right. But you're picking out only a subset of those tableaux. Yeah. Yes?
Yeah. So you said that you can do root expansion in a sure positive way if you're careful in some circumstances.
Yeah.
Can you say more about that?
Yeah, so being careful means, so the question is about you can do root expansion to get sure positivity if you're careful. And yeah, the answer is, so being careful means choosing which root to expand on at each step. And that's kind of all, like, that's basically everything you have to know to sort of do root expansion. And in the examples that we know how to do it, right, that was found by kind of just, working on lots of examples, right? And it's in the example of the K-sure functions, it's sort of hard to describe exactly what happens. It's in our paper, it's a few pages, but so there is a precise rule. Finding that precise rule is kind of the hard part. Yeah.
So all the examples you covered are about symmetric functions, but a couple of the examples on this slide are for polynomials. Do you have any either partial progress or like families of Catalanified polynomials, like non?
Yeah, so that's a good question. So the question was about, are there any Catalanified versions of polynomials that are not symmetric functions? And the answer is yes. So in this paper on the connection with the sure positivity of the Catalan functions, we actually went to a more general class of what we called non-symmetric Catalan functions. Okay, and so there you replace this while symmetrization operator by a de Mesure operator indexed by any W, any permutation W, instead of the longest element. And so I guess those count as sort of, they're not symmetric functions, so I would say they count as a sort of Catalan version of polynomials. But these examples I've put up here, I don't know, so yeah. Yes?
So the root expansion reminds me of this combinatorial modular law that's come up in Hessenberg varieties and chromatic symmetric functions.
Uh-huh.
Do you know if there's a relation?
Okay, the question was whether this is related to a modular law that comes up in chromatic symmetric functions. I don't know if there's a relation. I've looked at that paper. I don't really fully understand it. I didn't notice a connection, but you could be right. So I don't know that very well, so it could very well be the case. Yeah.
So you mentioned the strong root order of the affine symmetric group, and the root ideals, these are maybe some pieces of inversion sets of affine permutations, but only some of them. Is there some way to extend the definition to get to get these functions for any dominant affine permutation?
Wait, so I maybe didn't fully understand the part about inversion sets. What do you mean by?
If you look at the inversion sets of certain dominant permutations, then this would look like your sort of order ideals.
Oh, okay. I'm not sure. I think I lost a little. Okay, maybe we'll have to talk about that later because that was a little complicated for me to answer right away, and we're running out of time. I see. Okay, so I'm not sure how I can summarize this question well. It's asking if there's a relation between this and cohomology that comes up in Hessenberg varieties. So I don't know of anything like this. I don't know of any direct connection between this and chromatic symmetric functions, even though sort of upper order ideals do come up in both cases. But that doesn't mean there isn't one. So.